Okay, welcome to grade 9 math. We're in unit 4, linear relations, and this is lesson 2, rate of change and distance time graphs. By the end of this lesson, you'll be able to use the rate of change to create and interpret distance times graphs. So, rate of change, we have talked about before. It's the rise and the run. So, we recall the rate of change is measured as the steepness of a line, and that can be turned into a rate. And we use how much it's rising by how much it's running. And that's just rise and run is a simple way to remember it because it rhymes a bit. But really, it's the vertical change divided by the horizontal change, or the change in the x divided by the change in the y. So we could write that. Um, a delta sign, I'll just say a little point here. A delta sign, a triangle, is change. The change in something. So the rise is the change in the y, how much we're going up and down. That's the change in the y. And how much we go side to side is the change in the x. So we divide that by the change in the x. Otherwise, how much it rises or falls, how much it runs left to right. We remember that moving upwards is positive, moving downwards is negative. And most of the time, if we go from left to right, we're moving in the positive x direction. Okay, so when we calculate rise, we're counting by our y scale the number of ups or downs, and we subtract the 2 points. For the run, we calculate the change in the x scale, or we could subtract our 2 values. So let's show it 2 ways. We will have a rise. Now here's the tricky part here. Notice that this is going up by 2's. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 18, a rise of 18. And that would be a positive 18. And then they wouldn't change it here to make it by ones here. So it's going 1, 2, 3, 4, 5, 6. And a positive 6. And so our rise and our run equals a rise of 18 and a run of 6. And we can reduce that. 6 goes into 18 3 times. There's other ways you could have did it. We could have did that in like a step case scenario where we went just find where it hits all these nice grid points. We could have said up 3 over, sorry, up 6 over 4. That doesn't quite make sense. Yeah. Up 2, 4, 6 over 2. So 2, 4, 6 over 2. So you could have had up 6 over 2. Oh, that doesn't work. 6 over 2. Well, that equals the 3 also. So we could have done it that way. All right, let's look at the next one. The next one said, what if you subtracted the 2 values? Okay, so you have to see, well, where are we at with our y? So our rise and our run would mean that we are going from one y value, subtract the other y value. So look where y is starting up here, starting at 14. Oh, and our run would be one run value and the other run value. So you can call those 1 and 2. Might be easier to call it 1 and 2. Okay, so our first top y value is 14, and we're going all the way down to 2. Subtract 2. What's our rise and our run? Well, our rise, you gotta, now you put, if you did 14 here, then you gotta start with this one. This has to be our point 1. This has to be our point 2. So down here is at 6. So notice that 6 and 14 go together. And then notice that 18 and 2 go together. So subtract 18 because it said to subtract them. Okay, well, 14 minus 2 is 12. And 6 minus 18, well, that's going to give us a negative 12. Okay, so if we do 12 divided by negative 12, that's going to be a negative 1. And that could be our rise and run. That's our rate of change. We could call that our rate of change. All right. So, two different ways of doing it. Simply counting your grid lines, or in this case, going by 2s, in this case, going by 1s, but counting your rise and counting your run and doing the division there. We can say rate of change. We can call that the ROC, rate of change. And here was simply taking the numbers. The two y numbers subtract each other. The two x numbers subtract each other. And that can work. And you're free to do both of those methods if you want. All right, moving along. On a distance time graph, like we did last lesson, the rate of change, or the slope in this case, we call it the slope of each segment, actually indicates the speed for that segment. So where the rise in the y, if you had a y-axis and an x-axis, this would be our distance. This would be our time. So the rise in the y divided by the run in the x, or the y over the x, the d over the t, would give us a rate of change. And that makes sense because you know that speed is measured in kilometers per hour. So something like, so kilometers per hour, distance over time. So some tips to remember when working with distance time graphs. Remember to use suitable units, particularly if they are given in the question. So if it's kilometers, hours, use those. If it's meters and seconds, use those. Note that the axes will be different scales with the units of distance and time. So not necessarily going to go by ones. Often our distances will be scaled quite higher than our time. Be familiar with the common measures of these. When performing calculations involving time, remember that there are 60 minutes in every hour. There's 1,000 meters in every kilometer. A negative rate of change represents a change of direction back towards something. So it doesn't mean you're slowing down, it just means the direction. So if positive is moving away from the start line, then negative would be moving back towards the start line. That's all we have to indicate from that. We don't need to think of it as a slowing down at all. Okay, so let's read this example. Adele determines that she can run a distance of 1,500 meters in a time of 8 minutes. Okay, calculate her speed in meters per minute, and then in kilometers per hour. All right, well, let's tackle those separately. So if speed equals the change in distance over the change in time, then her speed equals 1,500 meters divided by 8 minutes. So type that into your calculator, and we have 187 0.5 meters per minute. Okay, so that is a good way of doing it. I find that there's no easy way to jump from meters per minute to kilometers per hour. So we will do that one separately. First, what you need to do is convert. Okay, so 1,500 meters divided by 1,000 turns into 1.5 kilometers. 8 minutes, well, we have how many minutes in an hour? 60. So we have to have 8 minutes divided by 60 equals 0.13 hours. Notice that it makes sense that it's less than a full hour, right? 8 minutes is really not close to an hour. So it makes sense that it's about 13% of an hour. That's it. Okay, so then we can do this same conversion with these two numbers instead. So using the same idea over here, speed equals our distance divided by our time. Speed is 1.5 kilometers divided by 0.13 hours. So we get a rate of 11.25 kilometers per hour. There we go. So pretty tough to convert that to that, I find. So there we are. I'd rather do them separately. Okay, let's move on to the next one here. So since we know how to do our rise and our run, our rate of change, or we call it our slope, let's take each of these segments together, or one at a time. So Chris runs each day as part of his daily exercise. The graph shows his distance from home as he runs his route. Calculate his rate of change for each segment of the graph. Express your answers in both meters per minute and kilometers per hour. Okay. Express the answers right. Include the direction he is traveling. So we're going to make positive being away and towards being away. Now, there is actually a way that we can do kilometers per hour as a conversion. Okay, this to this conversion. So if you take how many meters are in so we can do a rate of 60 divided by 1,000 gives us 0.06 as a conversion rate. So when we get down to it, we can do that with our values. Okay, let's take the rate of change of AB. So why don't we pause the video and you try to find what the rate of change here is. All right, we'll come back now and notice that we're skipping by 100s here. So we have a rise of 100 and a run of only 5 because these are going by ones, these are going by hundreds. So we have a rise in y and a run of x. So our rise in y is 100 divided by x, or 5. So that gives us 20 meters per minute. All right, and we're going to convert that to 20 meters times 0.06, and that equals 1.2 kilometers per hour. That's pretty slow. That's a slow uh, speed. Okay, we'll separate these so we don't mess up our math. Okay, so BC, B to C. Okay, so check your rise over your run. You pause the video and try that on your own. All right, once again, we can get started. And so we're going from 100 to 800. So you might say our rise, our change in y over our change in x equals 800 minus 100. You always start at where you're going, subtract where you've been. Where you're going, subtract where you've been. The change in x, however, is this number. That must be 11, 12, 13. And we started at 5. So 13 minus 5. So 800 minus 100 is 708 over 8. So multiply that, or sorry, divide that, and we have a rate of 87.5 meters per minute. We're going to need a little bit more room here. And we're going to multiply that by 0.06. So again, notice I'm doing conversion in red to sort of keep you focused on that's what we did. 0.06 equals 5.25 kilometers per hour. Now that's a decent jog. That's not a bad rate at all. Okay, and that's a big part of his run right there. So, all right, CD is a very small segment there. Maybe he's getting tired. Notice that not so steep, that's slow. More steep is fast, and less steep is slow again. We talked about that last lesson. So try to find your slope of CD. You can pause the video or continue listening with me. All right, we're going from a rise of 900. Well, look at this. We're only going up 1. That's pretty easy to remember. So we're going a rise of 100, and we're dividing by a run of, so a rise of 100, a run of 1, 2, 3, 4. So that's easy. 100 divided by 4 is 25 minutes, or meters per minute. Okay, so we want to convert that. So 25 times 0.06 equals 1.5 kilometers per hour. All right, good. We got 2 more line segments to go. So hopefully we'll have enough space here and not lose image of our picture. All right, well, DE could be tricky if you overthink it, but what's really happening there at DE? What's my rise? Well, my rise is I'm not rising a whole lot, am I? I'm not really going anywhere. So a rise of 0 and a run of 1, 2, 3. Well, that's not going to matter too much. So that's 0. He's going 0 meters in, doesn't matter how many minutes, in 1 minute. And if we convert that, well, that's not very exciting. 0.06 times 0 is 0 kilometers per hour. Obviously, he's at rest. That's the thing. He's at rest. He's not moving. So hopefully that didn't trick anyone. All right, here. Now, if we are going in a positive direction, then this way will be a negative direction. He's going back home, basically. His distance from home. So we started way up here. at looks like 900. Yeah, so 900, and he's going to be all the way back to 0, minus 0. And then from here, he's starting at 200, and he's going to, that looks like 29. 29. So 900 divided by a difference of 9, negative 9. Now it makes sense that there's negative because we are going back towards home. What does that give us? Well, that's going to be easy. 900 divided by 9 is 100, and he's going negative 100 meters per minute. All right. We're going to multiply our 100 times 0.06, and we get 6. Don't forget the negative. 6 kilometers per hour. He's going faster. So to get home, he went faster. He must be, finding that extra gear, as they say, in running. All right, so that's it. Breaking things up into step by step, segments at a time can break down our rates of change, our slope. In this case, speed. So if we're talking about distance and time graphs, we're definitely interested in speed. Okay, the next one is a driver leaves at 8 a.m. and drives 120 kilometers by 9:30 a.m. From then until 10:30 a.m., she travels at a constant speed of 50 kilometers per hour. After that, she drives at a constant speed of 100 kilometers per hour and then arrives at her final destination at 12 o'clock. All right. Draw a distance time graph that represents the trip. Include proper labels. Okay, so if we want to label this first, we have her hours since 8 a.m. So you could start this at 8 a.m. and then every hour, right? Could be 9, 10, and that kind of helps us gauge where she's at in time. Use military 13. Okay, and this would be distance home, distance from home in kilometers. All right, so a driver leaves at 8 a.m. and drives 120 kilometers by 9:30. Okay, so 120 kilometers. These are going by 20s. Notice that 20, 40, 60, 80, 100. So 120. Okay, by 9:30. Well, that's 9. That's 1.5 hours after she departed. Okay, so there's one. Okay, uh, from then until 10:30, she travels at a constant speed of 50 kilometers per hour. Okay, so for the next hour, she's gonna go at 50 kilometers. So where would be 50 more kilometers? We're at 120, so we need to go to 170. So if this is 20, 40, 50 is right here, and that's 1 hour. And they made it easy on us where they said from 9:30 to 10:30. So that is 1 hour. So that's good. Okay, from that point on, after that, she drives at a constant speed of 100 kilometers per hour and drives to the final destination at 12:30. So what would be 100 kilometers from this point? So from 170, she's going to go to 270. 220, 40, 60, 270. And it's too bad it's right in between there. So, and that's in an hour. So 50 kilometer, or no, 100 kilometers in the next hour. So she was at 10:30. So at 11:30, she'll be at this point. And then another 11:30 to 12:30, we need to go to 370. And she'll be at that point. All right. So draw a distance time graph representing the trip. Well, that's what we were doing together. So we get our line. So from here to here, from here to here, from here, and this has actually been a constant rate right up to the top there. There we go. So that's one way we can take the information we're given and turn it into a graph. After this, you have all your practice questions, and we can take those up. So you have rates of change of different lines. You have different line segments, trying to get the rate of change. Okay, different ones involving time. So remember, figure out what your zero start time was at 11 o'clock. So, and then time it from there. Okay, and more practice. You imagine what your school bus ride would look like. Pretty tricky because you're going to have to come up with your own scaling here. All right, so that's your practice. And you also have questions on knowledge hook that you can practice. All right, thank you for watching and see you next video.